I guess I forgot to start the recording. So yeah, he realized that this ray had mass enough to move something, and that it was deflected by a negative stream. So those were the observations, and then from that he could infer, he could draw a conclusion that this thing was made of little tiny particles, actual particles with actual mass that were negatively charged. Now, interestingly enough, and I sometimes like to think about how different the world would be had his original name for these little tiny negative particles stuck. Do you know what he wanted to call them? What he did call them? Corpuscles. Just doesn't have the same sort of zing. I mean, you know, electricity is the flow of electrons. And it's sort of a chicken or egg question. I'm not sure which. I think the name electricity came before the name electron. But had corpuscles stuck, and had we named the flow of electrons for them, it would be corpuscularity, I guess, that would run our lights and our computers and stuff. It just doesn't have the same zing. So that gets him to the point of realizing that there are these particles that are smaller than an atom. And once he knows that, what he proposes is what becomes called the plum pudding model. So Americans have no clue what a plum pudding is. And years ago, the first student who ever made a movie for me, whose 6-year-old brother starred in it, in the J.J. Thomson scene, the brother had a paper cut out of J.J. Thomson's face, and he had a bowl of pudding in front of him. And, you know, he's sitting there trying to eat pudding through a paper mask. It's not that kind of pudding. This is like a steamed cake, which sounds utterly disgusting, and honest, it's actually better than it sounds. I've had steamed puddings. So it's sort of like this. If you imagine a blueberry muffin or something, there are little tiny blueberries spread out throughout it. It makes more sense to modern Americans to say the chocolate chip cookie model, that the chocolate chips, the little points of negative charge, are spread evenly through this larger sphere. And so, you know, in that model, the cookie dough is the positive charge, the area of positive charge, while the chocolate chips are the little tiny points of negative charge. Well, it's not a terrible explanation. I mean, and it starts to get to the fact that the atom is made of smaller pieces, and that's useful. Interestingly enough, did anybody run across the name of the lab that J.J. Thomson was working in? Anybody notice a name? I ask because it comes up again and again and again. I think one person had it, Cavendish Lab. The Cavendish Lab at King's College, I'm going to get this wrong, Oxford or Cambridge. It's one of the very, very, very old universities in England. And this is a university that has existed since medieval times. And the Cavendish Lab comes up again and again and again and again. It's a laboratory within the university, and at the time that J.J. Thomson was doing this work, he was running the Cavendish Lab. Now, interestingly enough, and this is a name who you're going to see in a little bit, one of his students was a young farm boy from New Zealand who showed a lot of promise, who came all the way from New Zealand on the other side of the world, that's by Australia, to study and work in the Cavendish Lab by the name of, Ernest Rutherford, who then ends up running the Cavendish Lab later in his career. So Rutherford is a student of Thomson's. Well, that makes the next bit rather awkward, doesn't it? Have you heard anybody say, and I know if you had Mrs. Haylett for biology, you heard her say, in science we never prove anything. We only disprove things. In science, the whole idea is that we keep picking away at what we think is how things work to see if we can break it. Well, if it does work this way, then this should happen. See, that's not how it works. That's the process of science. So Thomson comes up with this. He observes these cathode rays. He makes an inference, and he creates a hypothesis about the structure of the atom. It's a model. It's a working explanation. This is how we think it works. Well, interestingly enough, let's summarize one thing here. So we've moved up a step in the world. We have Dalton's atom, which is this monolithic chunk of stuff, indivisible, nothing smaller than that. And then we have Thomson's atom, which adds the idea that, well, actually, it's made of different things inside. And it's sort of like a creamy positive batter, for lack of a better way to describe it, with these little negative chocolate chips scattered throughout it. Okay, so we're up to our second model of the atom, the plum pudding model, chocolate chip cookie model, whatever you want to call it. So remember that one of the things Thomson noted was that these pieces had actual mass. They had physical mass. They were actual bits of matter because they could move an object. And it takes mass to strike an object and accelerate it. So Robert Millikan, who's one of the few Americans in this whole list, I believe he was an Illinois farm boy, if I recall correctly, he devises what's called the oil drop experiment. And Thomson had tried to do something like this. He had tried to figure out how much these little tiny negative particles weigh, basically. He had tried to determine their mass, and he had tried to figure out how big their charge was, what the magnitude of the charge was. He was using water droplets. And there's a problem with using water droplets for repeated observations. What happens if you spray water into the air? It evaporates pretty quickly. So tiny little droplets of water tend to evaporate fairly quickly. Millikan designed a real similar experiment, but what he used instead of water was oil, which doesn't evaporate quickly. So he took a container, a lot like this. It was sort of a two-chambered metal container. The top and bottom of the lower chamber were charged. He basically hooked a battery to it. So he gave one plate a positive charge, one plate a negative charge. He sprayed this stream of oil drops across the top plate and allowed for a tiny little hole that those oil drops could fall through. So you have these teeny, teeny, teeny little oil drops. And then he would charge the plates. So the oil drops would become charged as they pass through that small opening. What happens to things that have an opposing charge? Opposing charges, opposite charges attract. Like charges repel. So he's got these little charged droplets in the middle, and he was able to, by playing with the charge on the two plates, get them to a point where they were suspended right in the middle. And he could have them hover there in the air. Attracted by one plate, repelled by the other, hovering. And what that allowed him to do was figure out the ratio of charge to their mass. Why could he figure out anything about mass? Because falling objects fall predictably. This is something we do in physics all the time. We know the rate of acceleration due to gravity, and we know how that's related to how an object falls based on its mass. Cool, that's easy. So he could get them to a point where he was balancing the gravitational force and the electrical force. And that allowed him to figure out the mass of the charge, because he knew the mass of the oil drops. So that little charged particle, he could then figure out the ratio of the mass to the charge. And he did this repeatedly. He got a mass of 9.1 times 10 to the negative 31st grams. 10 to the negative 31st. What's the biggest prefixed unit you used? The smallest, rather. Prefixed unit you used? Pico? Just times 10 to the negative 12th. This is almost 3 orders of magnitude multiplied. So this is like times 10 to the negative, fourth picograms? It's not even a picogram. It's tiny, tiny, tiny. He figured out the charge as 1.592 times 10 to the negative 19th coulombs. Coulombs is the unit for charge. And that's actually pretty close to the value that's the modern accepted value. He got really close with really primitive equipment. You don't have to say a whole lot about Millikan in the oil drop experiment. It doesn't connect well, but he couldn't have done this work without Thomson, because it was only after Thomson had done his work that we were sure that these things were actual particles with actual mass with charge. So here's where we get into the world of inferences. So once we know that there are negatively charged tiny particles in the atom, But we know that atoms are neutral. So if they're overall neutral and we have pieces of negative charge, what else has to be true? Well, there has to be something positive balancing out that charge in order for them to be neutral overall. The other thing is the fact that we know atoms have mass. I mean, the actual mass of an object you pick up is because of the mass of its atoms, and we know that things have mass. So if these electrons weigh so little, there has to be something else inside the atom that's giving it all that mass. Okay. Doesn't get us anywhere, but it gets us to some good questions. Questions like, what are the positive particles? Where are they? How massive are they in relation to the electron? Good questions. So in 1911, and actually I think the date on the research is maybe 1908 or 1909. I'd have to go back and look. Very often you'll find two dates, and they're very often the first date being when the research was conducted, Gesundheit, and the second being when it was published. So remember that in science we share information. Once scientists have some sort of result that they can interpret, in order to share that result with other scientists, they have to publish. And that publication allows other scientists to attempt to replicate their experiment. And we're going to talk about some scientists who replicated others' experiments to good end. So anyway, somewhere around 1910, Rutherford, Ernest Rutherford, who I believe at that time was already head of Cavendish Lab or in a senior position in Cavendish Lab, with Geiger and Marsden. Does the name Geiger ring any bells? Has anybody ever heard of a Geiger counter? Guess who it's named for? Geiger. Franz Geiger, I believe. And Geiger and Marsden were graduate students working for him. So they were working in the Cavendish Lab. They went on to their own careers, though. We don't ever hear of Marsden again, so I don't know what Marsden did. They took a piece of gold foil. Now, when we say gold foil, you've all seen this stuff. And you take for granted the fact that we call this, what? Aluminum foil. But a foil is a sheet of thin metal. One of the characteristics of metals are that they are what? Malleable. Able to be pressed and stretched into thin sheets. Characteristic of the material. Look at how thin that is. Now, this is a whole lot thicker than the kind of gold foil they used. The gold foil they used was, in essence, a single atom thick. And you can purchase that kind of gold foil from a science supply company if you wanted to replicate the Geiger-Marsden-Rutherford experiment. So they took what are called alpha particles, and these had been discovered by Rutherford, though that's not why they're so important. They took alpha particles, which are a little tiny, positively charged particle. They didn't know what alpha particles were made of at the time. And they shot them at the foil. Pew, 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 pew. Cool. Sounds like fun. And they had behind it a little screen that would light up every time something hit it. So you see very often this as the setup. So this is the gold foil, and this is the phosphorescent screen. And they put a little source of alpha particles here, and they shot alpha particles at the screen. Now, what they expected to happen? Well, what they expected to happen is, if we think back to Thomson's model of the atom, they figured that those alpha particles, which are positively charged, and they knew that. So you got positively charged things passing through a field with little points of negative charge. They figured that these things would go in, and they would kind of wiggle around, and they'd get deflected a little bit. But for the most part, they would probably pass pretty much straight through. That you would have some minor what's called deflection, because they would be sort of being pushed around by the negative particles. But overall, most, because remember there's that phosphorescent screen out here, most of their strikes would be out here. That's what they figured would happen. That's what they expected to happen. You always go into any kind of experimental setup with a hypothesis, what you expect. Guess when we learn the most? When you get something totally unexpected. So what happened instead is that most of them pretty much went straight through. There was very little deflection. So instead of seeing strikes all along here, and I'm going to shrink this, or at least move it, and we're going to leave the inside of this atom sort of a mystery, because it was a mystery to them. Instead, what they saw was mostly strikes right straight ahead, with a few. So we had mostly things that went straight on through, straight on through, straight on through, straight on through. And then about 1 in 800, instead of going straight on through, did this crazy thing. Whoops. Pow! What? Rutherford at the time said that it was as if you had fired a rifle at a sheet of tissue paper and had the bullet bounce back at you. They were shocked by this. They were astounded. Actually, I think what he said was it was as if you had fired a shell, meaning like a cannon, at a sheet of tissue paper, and it bounced back. It was absolutely, utterly shocking, not at all what they expected. So now he has to figure out what's causing this. Well, if, in fact, all of these are going straight through, there can't be any negative charge in a lot of the atom. 1 in 800 came straight back at them. Tiny fraction. So what does that start to point to? Well, it starts to point to a region of positive charge that is dense and small. That's tiny, 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 but densely positive. So instead of, and I'm sorry, I was mistaken. These are, of course, positive. So they would actually be pulled by the negative. But they would, for the most part, because the negative and positive were assumed to be balanced out, they would pass mostly through with some wiggle. But that's not what they saw. They saw them pass right straight through as if there were big regions of empty space, which, of course, is what we know about the atom, that there are, in fact, big regions of empty space. And a tiny, tiny, tiny fraction of the space inside the atom must be dense and positively charged. So that leads them to inferences about this tiny, positive, and they call it a nucleus, which actually comes from the Latin or Greek for nut, a little tiny kernel inside the atom that repels these positive charges. What Rutherford then proposes is often called the planetary model, because he imagines that electrons are like little planets orbiting this nucleus, like planets orbit the sun, that the nucleus is this tiny positive center, and that there are tiny little electrons out in orbit. So we've now changed our model, once again, from that monolithic Dalton's atom to the sort of chocolate chip cookie that Thomson proposed, to this planetary model, Rutherford's model. The biographical bits are not necessarily important, but I think they're interesting. I try to read one biography of one of these particle physicists every year because they're interesting people. Rutherford, as I said, was a farm boy from New Zealand and one of, I don't know how many kids, a bunch of kids. There was no money for him to go do anything, but he was super bright. And it was because of sort of his intellectual curiosity and his work, he ends up getting invited to Oxford or Cambridge, I think it's Cambridge, to study, and ends up running the Cavendish lab, ends up being a Nobel Prize winner in physics. Not bad for a boy, and I found this quote one year, and I have not been able to retract the source, but Rutherford is said to have quoted his mother as telling him, "Well, Ernest, we haven't the money, so we must try harder." And it was that kind of like farm, I always think of it as universal farm kid resourcefulness, having grown up with a farm boy dad. Well, what's laying around? Well, that's what we'll use to fix it. And it's a good approach to life. Well, I don't know. What do we have laying around? That's what we'll use to fix it. And probably because of that, Rutherford was highly prized as an experimentalist because he was great at walking in and thinking about, well, I don't know, what do we have laying around? Let's cobble something together. because he was incredibly resourceful with equipment, and he was great at setting up experimental apparatus. I mean, that's a pretty genius apparatus. Let's figure out what's in the atom by shooting particles at a sheet of foil a single atom thick. It's pretty clever. And that was kind of the hallmark of his career, was this, this ability to sort of think on his feet and design apparatus and experiments that would really get to the heart of what you needed to know. Okay, now, here's the problem. Everything we find out raises a problem. What do opposite charges do? Attract. Yes, yes, they do, as a matter of fact. So, we're saying that there is some kind of positive charge, and all looped around it are these little negative charges. Well, why don't they just get sucked into the positive? No, seriously, why don't they? Rutherford couldn't answer that either. That was a big problem. So, you know, he proposes this model, this planetary model, but he says, yeah, we're still really not sure about this piece. Keep going. Keep going. We're going to round out the work on the nucleus before we jump to those pesky electrons and the problems with them. And that is James Chadwick, who's not the first name on the slide. I used to include the Joalette-Curies on the rubric. I kicked them off the rubric this year because they really did get people confused. But I'm going to mention them anyway because I think it's a great story. Does the name Curie ring any bells to anybody? Madame Curie, Marie Curie, famed for her work with radioactive material. She, of course, died of cancer in her 50s, I think, because of her exposure to radioactivity during her research. Her daughter, Irene Curie, sort of inherited the family knack for science. As a matter of fact, and this would have been in like 1910, 1911, Irene and her, I forget how many siblings, because Madame Curie was busy on many fronts, scientific and reproductive, the Curies and several other families of notable scientists just started a school for their own kids where their elementary students were taught by people who had PhDs in science, because, you know, why not? Wouldn't that be awesome? So anyway, Irene grows up in this kind of atmosphere, grows up working in the lab with her mom as a teenager, goes on to meet Frédéric Joalette, I don't know, I'm probably mangling the pronunciation on that. And they fall in love. They meet because he's working in her parents' lab. He's an assistant in the lab, and he kind of meets the boss's daughter, and bosses plural, because Pierre and Marie Curie ran the lab together. So Frédéric and Irene decide to get married. Here's the fascinating part, and this is in the 1920s. They adopt a single last name. They hyphenate their last names. They both take the surname Joalette-Curie, and they publish for the rest of their lives. They do research together and publish together only under the surname Joalette-Curie. Now, egalitarian? Sure. Sure. You don't have to change your name. We'll both change our names. Awesome. In Frédéric's motivated self-interest? Sure. Doesn't hurt to have the last name Curie if you're working in the sciences. You know, doesn't hurt to adopt your in-laws' surname when your in-laws are Nobel Prize winners in physics and chemistry. Irene and Frédéric have a rather speckled scientific career because they keep getting it wrong. They do research on a number of topics. And 3 or 4 times, they miss winning a Nobel Prize because they misinterpret their own results. So one of the things that they did was that they were looking for components of the nucleus, and they fired charged particles at wax. And they were seeing particles that were kicked out. They were seeing particles ejected from the wax. And so they did all the research. They published their findings. Chadwick, in 1932, reads their research and goes, oh my God, they don't know what they're looking at. He recreates their research, gets the same result, but understands what he's seeing and is credited with the discovery of the neutron. He finds that neutral particle that's the missing piece for mass inside the nucleus. And it's because the Joliette-Curies didn't know what they were looking at. So you have to not only have the observation, you have to infer correctly. You have to infer correctly, or you miss the boat. Interestingly enough, Chadwick spent most of World War I in a prisoner of war camp in Germany because he had the misfortune in January of 1914 to travel to Germany to work, I believe, perhaps with, I don't know if it was Max Planck, whose name also comes up again and again. But he traveled to the continent from England, he was British, to work in a lab in Germany and was caught there when World War I broke out, and ended up spending the next 4 years in a prisoner of war camp as a prisoner of the Germans. So, interesting stuff. What's really interesting about that is the fact that there were other scientists from the same lab who were in the same prisoner of war camp, and they devised experimental apparatuses out of things like, basically gum wrappers and coffee cups. They jimmy-rigged all kinds of stuff to continue to do research. They organized a lecture series for themselves to continue to learn and grow from one another, because you can learn anywhere you are, including in a German prisoner of war camp for the duration of World War I. Why don't electrons get sucked into the nucleus? This is where we're going to stop today. And tomorrow we're going to pick up with this. Why don't, if you have a positive charge here and a negative charge here, why don't they collide? You take two magnets with the opposite poles and you hold them about so far together, what happens? They collide. Why don't electrons get sucked into the nucleus? So tomorrow we're going to start talking about observations starting in the late 1800s, in the late 19th century, and going all the way up through the eve of World War II that get us to the modern structure that we know. And just to recap, we've got the Daltons. We got Dalton's atom. We got Thomson's plum pudding model with its little bits of negative charge. And now we're working with this. These little negative charges orbiting the nucleus, sometimes called the planetary model, sometimes talked about as Rutherford's planetary model. So that's where we stop. Tomorrow we build our final two models.